Okay. Hey guys.
Heyo.
Who all do we have here? Is it just you, Nick?
I
Okay.
think so.
There were 2 other people that requested an additional office hour, so I invited them to this meeting as well. So there might be a few other folks showing up. But while we're here and it's just you, let's take
Good stuff. I was, or had been at least working through some of the IVP, like almost a full binder worth of notes already, which isn't necessarily a good thing. It just means that I write down a lot of stuff. But I've been working through some of this IVP things, and like the first 4 problems that they have on the homework, where it's kind of like basic level, recognize that you're, recognize what the U and the DV and all that substitution, how that works. I got those, but when it got to more interesting U subs, where it was like cosine to the -1 dx, I was like, I can see how you might set that up as 2 separate functions, but I wasn't sure how it would play out.
Oh, okay. Yeah, so the trick for that is going to be the Lipet rule. So the cosine with the -1 power there, let me switch over to my dot cam real quick. Are you familiar with that notation? Is that
the Lipet rule or just the cosine -1?
The cosine -1. Are you comfy with that? Do you know what that means? Some people use a different.
Yeah, it's. Some people say arc cos or cosine -1 or inverse cosine.
Right. So it's not a power, right? That's the big thing to make sure we're with there. So cos with the -1 of x here. To say that is equal to y. Let me zoom in a little bit more. This is the inverse cosine function. So this means 2 things. First, it means that x is equal to the cosine of y, and that 0 is less than or equal to y is less than or equal to pi. And it's the arc cosine, the inverse cosine function, right? Which is different from the 1 over cosine or the negative power. So this is an inverse function, right? That's the idea. This is the inverse
of the cosine function.
Right. So if you follow your Lipet rule, the problem in question there is to integrate the inverse cosine of x dx, right? If you follow your Lipet rule, he will tell you what to do. So we ask, are there any logs in this? And there aren't. So we go on to the next guy. Are there any inverse functions?
Yeah, inverse cosine.
Yeah, there are, right? So that means I'm going to get u to be the inverse cosine of x and dv to be everything else. That's how the Lipet thing works. So this tells you how to pick u, and then dv is always whatever is left over. So according to my Lipet,
that's a better way of thinking about it.
Yeah, it's super helpful. Knowing how to pick u doesn't help if we don't also know how to pick dv, right? So the nice thing about it not only tells you how to pick u, it also tells you how to pick dv. So I'm going to run IVP with u equal to the inverse cosine of and dv as everything else, which in this case is just dx. I heard someone talking to you. If you need a minute, that's okay. Just let me know.
Oh, you're good. It was my little brother wanting to show me something. It's all good.
No problem.
So, yeah. So you've used cosine -1. So I guess I can get that far. I see that dv is just equal to dx. So then when you, I guess, try and solve for v, or not try and solve for, when you, I guess, take the antiderivative of dx, is it just v equals x?
Yes, sir. Yep. Yeah, okay. You've been integrating on both sides. If I integrate dv, that gives me v. If I integrate dx, I get x.
Is it? Yep. Sweet.
So the trick,
and then
remembering the derivative of the inverse cosine function. This is a little bit wonky. Do you remember this guy?
Is this the 1/2 times, is it 1 minus sine x or cosine? It's one of the funkier ones.
It is a little
like that.
It's an algebraic function. So it's -1 over the square root of 1 minus x squared.
Oh, Lord. Okay.
So the way I remember this is that it's just the negative of the derivative of the inverse sine function. So it might be worthwhile to take a second and add to your notes these derivatives, right? The derivative of the inverse tangent function, that's 1 over 1 plus x squared. The derivative of the inverse sine function, that's 1 over the square root of 1 minus x squared. The derivative of the inverse cosine function is the negative of the derivative of the inverse sine function, so it's negative 1 over the square root of 1 minus x squared. And then secant and cosecant work similarly. The derivative of the inverse secant function is, and you won't see this a lot, it's 1 over the square root of x times, sorry, the absolute value of x times, and honestly, I have to double check to make sure I don't fuck this up myself. I think it's then the same square root piece here, but let me make sure. Yeah, sorry, u squared minus, yeah, so this will be x squared minus 1, like this. So 1 over the absolute value of x times the square root of x squared minus 1. So a similar looking square root, just subtraction in a different order. And then the derivative of the inverse cosecant is the negative of the derivative of the inverse secant. It's negative 1 over square, absolute value x times the square root of x squared minus 1. The bottom two we don't really use a lot. These top two we use often. So I would make sure.
I need to be familiar with those.
Yep, make sure you know the top two. And then the bottom one, this third one here, we use this sometimes, but he's pretty easy to remember if you remember the sine one. You just remember that it's the negative of the sine one. Kind of like the forward derivatives, right? When you differentiate cosine, it works the same way as differentiating sine, you just get a negative.
Yeah.
Same sort of thing. So I would tuck those top two away. Make sure you remember those.
Yeah, got them written down and highlighted, so hopefully next time I'm looking through this section, I'll remember to take another look at those and work on them some.
Cool. Yeah, yeah. And this stuff will be relevant in the trig subsection too. Oh, here, I'm sorry. Can you give me just 1 second? I'll be.
Yeah.
All right. So we still need to do the IBP, right? We've got our IBP table now. We've talked about those derivatives, but really, this is what we need to do.
So now we actually set that up. So it's uv minus, oh no, hold on. I have it written here.
You got it. You're saying it right. Keep going.
It's uv minus the integral of v du.
Perfect. So that's u times v. That's the inverse.
Cosine negative, or inverse cosine of x times x, or x cosine inverse of x, minus the integral of cosine inverse of x, and then dv is just dx.
So it's u times v.
Mm-hmm.
It's the integral of v, which is x, times u.
Oh, v times du, gotcha.
Times negative 1 over square root 1 minus x squared dx. Sorry, and my du here should have a dx on it. Yeah, so that's our IBP output. And then we can clean this integral up a little bit.
Yeah, there's some negative signs to be shuffled around and whatnot.
Yep, and I like the way you said the first piece too, x times cos inverse x. Somehow that just looks nicer to me. So this negative can come out, and it'll make the integral positive, and then we'll have x over the square root of 1 minus x squared dx, like that.
Okay, and then let's see, for this one, because it's a indefinite integral, we can simplify it down some by taking the antiderivative. If we split these up into, what's the term for it? Separate them up by power functions?
Well,
almost.
Unfortunately, the algebra of this thing, I can't really do any more simplification here, right? Like,
yeah.
Sorry, my dog's going nuts because the lawn care people are outside.
You're good.
So because this square root doesn't play nice with this subtraction.
Oh, yeah.
I can do here.
That doesn't work.
But what I can do here is a little substitution. If I substitute for the thing under the radical, then the derivative of 1 minus x squared is negative 2x. So I've got an x up here, which will allow me to make that substitution work. So the next move here is going to be to let z equal 1 minus x squared, the stuff under the square root.
Okay. And then dz equals minus 2, negative 2x. And then if you put a negative 2, or no, a negative 1/2 outside the integral, and you put the negative 2 on top of that fraction, right?
Yeah, I would think of it like this. So x dx, which is the piece I have in my integral, is equal to negative 1/2 dz. You can do it like you said too, where you multiply by a 2 here and a 1/2 out here. However you get there is okay with me.
Gotcha.
This is probably the cleanest way to think of it. But whatever works best for you is okay, as long as you arrive at this. So we'll have our x cos inverse x out front, and then minus 1/2 integral 1 over z dz.
1 over z dz.
All right,
wait, wouldn't it be 1 over the square root of z?
It is, yeah, I'm sorry. 1 over root z, yeah.
Okay, and then that's as simplified as it gets, because we've got that x cosine, or x inverse cosine of x, but we can't do much with that, I'm not thinking.
Yeah, we're happy with this.
And then we have to add our constant of integration there, and then that's that.
Well, so before, we need to actually do this integral still, right? So we made a substitution.
Oh, shoot, yeah.
Make this integral easier. But now that this is just 1 over the square root of your variable, no like wonky business down here, I can write this as a power function.
It's z, or z to the negative 1/2.
Yeah, exactly. Yep, just like that.
And then that turns into z to the 1/2 over, or divided by 1/2, or 2 times, is it square root of 2z?
It's 2 times the square root of z, but if you're ever
okay,
the way you said works great, and there's nothing wrong with doing that.
Okay.
So if I had any doubt about what that looks like, I would write it exactly how you said it. Z to the 1/2 divided by 1/2, and then we'll simplify.
Okay. And that's where you add the constant of integration, and then if that's what you could put in a WebAssign, it would say, yep, that's good.
And then the only thing we need to do from here is go back to this. Go back to our...
Oh, plug in the...
Yeah, the x.
Yeah.
We can simplify.
As we have.
Dividing by 1/2 is the same as multiplying by 2. And then z is 1 minus x squared. So we get this. And this 2 and this 1/2 can cancel. So my final answer here would look like x cos inverse x minus the square root of 1 minus x squared plus c. That's how I would write that.
Okay. So that works. That's a lot clearer now than what I was thinking it would look like.
Good, what?
Okay.
Okay, so what else can we look at?
Let's see. There was, so with that same trick, a lot more of these look feasible now. I mean, there's a bunch of these that are like natural log of something, but
So
those are just functions inside of functions.
let's just try whatever the next one is that you haven't done yet, and I'll let you talk me through it, and we'll make sure everything feels good.
Okay. So here's one I get stuck on. It's the integral of ln, or natural log of the square root of x dx.
Ah, cool. And it's an indefinite integral like that?
Yep.
Okay. So what you thinking?
So what I'm seeing is we have natural log of a function. So there's two functions. There's a natural log of something, and then there's the square root function, which we can see as kind of separate almost.
Well, the square root is inside the natural log here, so we can't really separate them, but you can think of them as the two different functions in play.
So what we could do then is, before we do, no, actually, IBP would just work right off the bat, wouldn't it? Because we have a log function that we could work with, or is it because we have the square root?
So you've got two choices. You could try substituting like z equals square root of x and see if you can make that go. But I don't really have anything floating around here to use potential. So I think diving right in with the IBP is probably the most natural choice.
So we want u to be, this is L is log, so ln of, would it be ln of x, or would we do the whole thing at ln square root of x?
It has to be ln square root x, because that's what we've got.
Okay.
Real quick observation.
Yeah.
I don't know how much you remember about, let me come to the side here, about rules for logarithms. Do you remember any way to simplify expressions that look like this?
Oh goodness, yeah. There was basically, this was literally my entire Algebra 2 class, and I'm drawing a complete blank. It was base, answer, and exponent were the three components. I just don't remember where they were. Log, base,
Power is inside
of the answer equals the exponent.
That's true. That's true. But when it comes to just algebraically manipulating log expressions, if you have a log of some number raised to a power, that's the same as that power out front times the log.
Oh, okay. I was overthinking this.
Yeah, no, it's okay. So if we wanted to,
we could write it as 1/2 ln of x.
Yeah, and I think 0 people in your class saw this, so don't feel bad if it didn't jump out at you, because everybody's thinking about the integration stuff. But sometimes it really pays dividends to think about what you can do algebra-wise. Yeah, this 1/2 power can totally come down. So this is the integral of 1/2 ln x dx, and then that 1/2 can come out.
Yeah.
So if you are supremely lazy and a little bit clever, will give you a much faster path to the answer.
Okay, so that gives us that substitution, which makes that a bit simpler. We still have we still have to take the derivative of that for du, and then we have to have v equal x, or dx, which means that dv would be equal to x.
So let's run through it like this, and then we'll run through it the other way, because this way is going to give you better practice with your IBP. This way is going to be much faster though. So we'll run through it the fast way first. Like you said, u would be ln of x, and dv would just be dx. What is du?
Du derivative of 1/2 natural. Crap.
So we'll pop the 1/2 out front. We don't even need to worry about the 1/2, like this. So yeah. I'm just worrying about integral.
Derivative of ln of x is just 1 over x, right?
Yes, sir.
Because the derivative of the inside of the function over is just the inside of the function.
Exactly. Yep. So du is 1 over x dx, and v is just x. So that's my little IBP chart. And according to that chart, my integral, I've got a big 1/2 out front, this 1/2. So I write the 1/2 and then open up a paren.
So you're cutting in and out a little bit.
Oh, I'm sorry.
Okay. There you are.
Okay.
At least the camera's coming through clearly now.
Good. So I've got this 1/2 from the front of the integral, and then I'm going to open up a parentheses and put my IBP formula in here. I'll have u times.
So we have, because it's, u times v, so 1/2 ln of x times x, or 1/2, or you just do x over 2, couldn't you?
You could. I'm going to leave the 1/2 all the way out front.
Oh, yeah. So x ln of x minus, and then we have integral of v du. So that's integral x times 1 over x dx.
Perfect.
So this is, I guess, another thing, because I always get stuck on these little algebra steps where it's just like, can I do this? Is this legal?
Right.
Type deal. So x times 1 over x, I want to say that it just turns into 1, but I don't feel like that's legal.
It's totally legal.
It is? It just works?
So think of the x as x over 1.
Oh, yeah.
Multiply straight across. So that's the same as x over x. And no matter what x is, as long as it's not 0, x over x is equal to 1. So yeah, that's kosher. So that integral is just the integral of dx.
Which integral, and with respect to x, kind of just zorps out to nothing, or to x.
Exactly, yeah. So this is integral of dx, and that's going to be the integral of dx is just x, and you can tack on your plus c at this stage.
And then you can probably leave the 1/2 outside, but to simplify, you can distribute that across.
Yeah, taste. You could distribute it or leave it out front. I wouldn't have a problem with either.
Okay.
Yeah, if you wanted to, you could write. You could write it like that if you wanted.
Okay. So that's where that one stops, it looks like.
It is, yeah.
Okay. There's one more, I think, in this section, or this type of problem that stumped me a little bit. Where was it? So it was parentheses, ln of x, parentheses, all squared. It was an indefinite integral.
This is a slightly more interesting guy. Again, we do have a logarithm.
But we also have a function squared, or the whole thing squared, so that makes it a little bit more interesting.
Yeah, so remember, this is the same as ln x times ln x dx, right? The square is multiply by itself. So you could pick one of these ln's to be u, and the rest of this to be dv, if you wanted to. Or you could pick the whole ln squared thing to be u, and dv to just be dx. Either one will be okay. I would be inclined to try this first. I would be inclined to try this setup and see where it goes.
Okay, so if dv equals dx, then du ln of x is normally 1 over x, but we can't necessarily integrate it just like that. We have to use the
Yeah, this is a chain rule.
product rule, or chain rule, yeah.
So that's 2 times ln x to the 1, that's the derivative of the outside function, the squaring function, times
1 over x.
Good. So this is my du.
And then dv is just x.
Yeah, when I integrate dv to get v will just be x.
Okay, and with that, we then set up the integration by parts. We have uv, so ln of x all squared times x minus the integral of, is it v du, right?
Yep. Yeah, so it's always
so x times
across. Yeah, so x times, and then we've got this big thing for du. That's 2
ln of x times 1 over x dx.
Looking good.
So then now we have that. Now let's see, how can we simplify the integrand there to the point where it's less monstrous looking for when we actually go to take the antiderivative?
I feel you. So I'll write the front as x ln x squared minus, everything in here is being multiplied, right? Everything inside.
Yeah.
Which means the 2 can come out. And then I have ln x times 1 over x dx. That multiplication can be done in whatever order you want. So just like in the last problem where the x
the x and the 1 over x cancel out, so we're just left with the integral of ln of x.
Mm-hmm. Yeah, exactly.
So integral of ln of x dx, and then the antiderivative of natural log. Crap.
This is actually an IBP thing on its own. So this requires 2 runs of IBP.
Okay. So then we set this up kind of like we did the earlier problem where it was the natural log of square root of x, except we run it as u equals just ln of x.
Yep.
Okay. IBP part 2.
Mm-hmm.
U equals ln of x. dv equals dx. du equals 1 over x, and then v equals x.
Good.
And then we run the whole merry-go-round again.
Yes, sir. This will be x times ln of x squared minus 2. And then I open up a big
minus big old parentheses.
And then inside these big parentheses goes the stuff from this IBP table. So that's u times v.
Write this somewhere where I actually have room. Minus 2, big parentheses, so it's uv, so it's ln of x, or x times ln of x.
Yep.
Minus the integral of u dv. So ln, no, hold on. That beans it again.
You got it.
v du. v du, not u dv.
Yeah,
That's,
c minus integral v du. Yeah.
so then that's x times 1 over x, which is just integral of nothing.
Or the integral of 1, yeah.
Yeah.
Integral of dx. So we get x ln x all squared minus 2 open paren x ln x. And then this is the integral of 1 dx, or just dx. And like you said, this guy is going to become an x.
So then we're left with something long and ungainly, but different than what we started with.
It's not too bad. And the nice thing is each step here, the integral in that line is getting easier, right?
Yeah.
Each step we take, the integral looks nicer and nicer. That's a good hint that you're walking in the right direction.
Okay. Let's see. And then is that pretty much where this one stops?
I would distribute the two, but then yeah.
Okay. So that one works. Let's see. And I got stumped on a few of the indefinite integrals. Or not the indefinite, the definite integrals. So like, where was it? It was number 11, I think, where it was the indefinite integral, or the definite integral from 1 to square root of 3 of arctan of 1 over x.
This is neat. All right. So what have you tried here? Or what are you thinking about?
So what I was looking at was I have inverse tangent function, which is the first thing that comes up when I'm thinking through the my pet rule there. So that's what I'm wanting to gravitate towards for setting up the IBP. And then 1 over x I'm seeing as the, whatchamacallit, derivative of natural log. So if that is, I don't think there's a way to set that as u, but that would be.
Well, so tan inverse on its own doesn't mean anything.
Tan inverse of something.
Yeah, we got to have something in here.
So tan inverse of 1 over x.
That's what we're going to pick for our u.
And then we have dv equals dx. So then du equals, so the inverse tangent was 1 over, crap, 1 over 1 plus x squared. Yeah. But it doesn't necessarily work that way if you have 1 over x.
Okay, so I'm going to make a small technical adjustment.
Okay.
My wife needs to use my webcam for something, but since we're just using the dot cam, this should be all right. So I'm going to pop out this webcam. I want you to let me know if you can still hear me, because the micro.
It no longer says you're muted.
Can you hear me at all?
Yep, we can hear you.
Sweet. Good.
Also, at some point, I think recently, we acquired Lucas, who joined in the office hour.
Howdy. I've been here for a bit.
Feel free to ask any questions.
I don't know what you just said.
Chat.
Okay, that works. Let me pull that up on the side. Okay. So I was looking at u being inverse tangent of 1 over x. Gotcha. So would you just take the term that you normally lose for like, oh, it's a chain rule? Yeah, because it's 1 over x. We have to take whatever the initial derivative term is with the inside term plugged in for x times the derivative of the inside term. So 1 over 1 plus 1 over x all squared times 1 over x prime. Yeah. And then the 1 over x prime thing, it's akin to like x to the negative ones. Well, yeah, it'll be similar to x to the negative 1. So when you take the derivative of it, you're subtracting another 1, so it'd become 1 over x squared for the right-hand side. So then du would be 1 over 1 plus, so 1 over 1 plus 1 over x all squared times 1 over x squared dx. And then the negative, yeah, because the negative 2 and it multiplies out front, right? Oh, it's the negative 1, so that multiplies and that makes it negative, yeah. Yeah. Okay, so with that,
Also I'm going to bring my mic on, and if you can't hear me something, let me know, I'll type it.
okay,
We need our dv.
dv is being dx, v gives us x, so that's our IBP for this one.
Good.
So now we can set this up. uv minus the integral of dvu, except uv, because it's a definite integral, has to be evaluated between the bounds, right?
Exactly. Don't forget the evaluation. Each piece gets evaluated. I'll have
So it's inverse or arctangent of 1 over x, or x times arctangent of 1 over x, evaluated from 1 to the square root of 3. And then my calculator. It's buried at my desk somewhere. There. Let's see, 1 times arctangent of 1 over 1. Or no, we don't have to evaluate it right now. We can just set it up to be evaluated and keep going, right?
evaluate in the next step. I would finish down this line.
X times 1 over 1 plus 1 over x squared times, it's the negative 1 over x squared dx. So that integrand is not friendly looking, but
Actually, nicely. Careful. So let's come off to the side for a minute and do some algebra. the same as top with the top and the bottom with the
I see that. Oh, yeah. Because it just multiplies straight across. So you can kind of sort of distribute that in a sense.
Before I distribute, write this as -1 over, I would square the 1 over x here. It would be 1 over x squared times x squared. We'll distribute.
Distribute the square on that term first, because 1 squared is 1, and then x squared on that fraction. And then you can multiply those out to the x squared. So you'd have x squared plus x squared over x squared. So just 1 over x squared plus 1.
Very nice. It actually becomes really, really clean, right?
Yeah.
Here.
So
Go ahead and do this evaluation.
that comes down. Now we can do the evaluation there. X. And minus the integral of x. Okay. So x times 1 over x squared plus 1.
Sorry, and this is still from 1 to the square root of 3.
Yeah.
So step, bring this negative front, that's a plus. X squared to make x over x squared plus 1.
So that lets us cancel out an x, so to speak.
So I can't cancel anything because there isn't a factor of x in the denominator. I would need
Yeah, because it's just x squared plus something.
So it's x squared plus x. You factor in x.
Then you would be able to.
Go ahead and have this evaluation. And then we'll
Okay.
this up. The arctan of 1 over root 3.
Goodness, it's been a while since I've done it in radians. It's
What's the unit if you want? It doesn't hurt.
Is it the it's the first angle, because remember it was kind of funky and I was trying to remember. It's the 30?
Which is pi over 6.
Yeah.
The inverse tangent of 1.
Inverse tangent of 1, the 45-degree angle, or pi over 4?
And here we'll have minuses make plus. Equal 1 to root 3.
Because you have 2 minuses. Okay. So now we have x over x squared plus 1. How can we write that in a way where we could Do we have to go through the, or do we have to do we can do a U substitution for this, right?
Good.
Simplify it down some. So we have z equals x squared plus 1, dz equals 2x dx. And then we also have to, when we do this, change the bounds. So when z is equal to 1, or when x is equal to 1, z is equal to 2.
Good.
And when x is equal to root 3, z is equal to 4. So then we have over 6 times root 3 minus pi over 4 plus the integral from 2 to 4 of, let's see, so we have z on the bottom of the fraction, then we have 2x, so do the same trick we did for the other problem where we had the 1/2 on the outside, because then we just have 1 over z dz.
So the x dx is 1/2
right?
z. So we get this guy.
Yeah. And then we evaluate, or we take the antiderivative of that last integrand there, evaluate it, and then combine terms, and then that's the answer. Because we have the antiderivative of 1 over z, which is ln, right? Yeah, ln of z. 2 to 4. And then natural log of 1/2 natural log of 4 minus 1/2 natural log of 2. Give me another few minutes. Sorry, buddy. Okay. This will probably be my last problem because I think I have to go here shortly.
Actually, since I also have limited time here, I'd like to see if there's anything you just wanted to look at, and maybe it would be helpful for both of you. Since we've people here, if real quick.
I didn't hear a whole lot of what you said other than the yes, that would it would probably be good to hear some from Lucas because your time window is also limited.
Yeah, I had some stuff I need to look at.
Go for it, my guy. I'm going to go ahead and get my stuff wrapped up, but I'll be here for the last problem or so. I do appreciate the help, Professor.
Wow, what was the
It's kind of an older problem. I again, I was still trying to get caught up with all the rules from Calc 1 before.
Yeah, that's okay. Let's.
I couldn't figure out how to do it was from homework 2, a problem 4.
Let's see.
Alrighty. I've got to skedaddle for a moment here. I will catch back up on you guys, or catch back up hopefully tomorrow.
That's good, Nick.
Have a good one, y'all. Thank you very much, Professor.
Me too. And if you got more problems. So homework 2, number 4, right?
No, I did not say homework 4.
Homework 2, problem 4?
Yeah. That looks like the right one.
So, first we need the graph of this function, right? Remember, y equals known. It looks like this. Minus over 2, 3 pi over 2, minus 3 pi over 2. I take this graph, shift everything, give me this graph. It's going to focus on that middle piece there.
Yeah, and it cuts off at y equals 4, right?
Y equals 4 is like up here. Let's see, they said they haven't told us exactly where it cuts off. They say they want us. Yeah, no, they have. They said y equals 3. I just didn't write that down. Y equals 3 would be like right here, and that's where they want us to cut. Want us to rotate about the line equals 1. So this is my region. Since this is coming from section 6.1, 6, we have to use the disk washer method. My strip could be drawn in perpendicular axis of rotation. Far? Little r is always the distance from the nearer end of the strip to the axis of rotation. R is always the distance from the further end of the strip, axis of rotation. Little r.
Yeah, I believe on mine, so it would be 3 minus, in parentheses, 2 plus secant x, which would just, or would it be 2? Yeah, 2 plus secant x, which would just be 1 minus secant x, right?
Would be the height of the strip. Height of the strip isn't actually what we're looking for. Remember, little r is the distance the nearer end of the strip to the axis of rotation, and r is the distance the far end of the strip to the axis of rotation. It helps me a lot to come in here and label these distances, trying to figure out formula for them. R is this y value, which is 1 plus secant x, because I'm on the graph of 1 plus secant x there, minus the value here, which is 1. So little r should just be secant x. Leave the way WebAssign randomizes the numbers, always be true, even if you had like 2 plus secant x instead. Make sense?
Kind of. I'm trying to figure out where you're pulling the -1 from.
So it's this y value right here, this y value right here. Y value right here is y equals 1, because that is my axis of rotation. Y value minus this y value, that will give me the distance.
Okay.
This y value is 1 plus secant x. 1 plus secant
I
x.
think. Oh, I understand. I understand. Okay, I get it. I get it. It's a relation that. Yep, I got it.
Cool. What about big R? Oh,
Big R, I believe.
Y value minus.
I had this one before. It was 3 minus.
Yeah.
Wouldn't it be 3 3 minus 2 plus secant x, I guess minus 1?
Just be only 2 y values here. So we're going to take this y value, which is 3, and we're going to subtract this y value all the way down here, 1.
Oh, okay.
So I actually don't care about the length of the strip. I don't care about this point. I just want the distance from the far end of the strip, axis of rotation. Far end of the strip is here, and the axis of rotation is here. So this point doesn't get involved. It's from here to here. It's actually constant.
Okay.
The end of the strip is always along the line y equals 3. The axis of rotation is always the line y equals 1. This is just 2.
Okay.
The dv And then finally, we're going to integrate dv to get v. Integrate from negative pi over 3 to over 3.
I'm pretty sure there's a specific what do you call it? There's a specific antiderivative of secant x or secant squared x, right?
Yeah. So think hard. One of your trig functions differentiates immediately secant x. One of them does. Secant squared x.
I remember there being some sort of rule or I think a video I watched said it or something when I was trying to like study this stuff. That if it's even or if it's the same length, you can just multiply it by 2 and drop the bottom to 0.
True. We can call this pi. Well, 0 to pi over 3. 4 minus secant x. We're using the symmetry there. This is symmetric about the y-axis. Take what we would get from the right half and double it. What about an antiderivative?
Okay. Well, can we just take an antiderivative here? Is this a spot we can? Yeah, because I don't think we need to use it. Do we need to use u sub? I don't think so.
We can take an antiderivative straight from here.
Okay. Couldn't we pull? Yeah, we can pull pi out. I didn't even notice that. Sorry, hold on. So it would be 2 pi the integral of 4 minus secant squared x. So it'd be 4x minus, I don't know what the antiderivative of secant squared x is.
Tangent.
It's just tangent?
For the derivative of is secant squared. The antiderivative of secant squared is tangent.
Okay. See, our my past calc professor, my calc 1 professor, barely went over anything trig. If anything, like out of all the problems on all the tests and all the homework, like maybe like 1 or 2 of them were ever trig, and rarely included stuff where we had to deal with this.
So let's take a second here and remember the forward derivatives of the trig functions.
That should be cosine, yeah. Derivative cosine is negative sine. Tangent, I guess, is secant squared, or yeah. Is secant cotangent or secant tangent? Yeah, secant tangent.
The two we don't use as often are cosecant.
Are those the important ones, or are there anything else that I need to remember?
I would remember all of these, and then also the inverse trig derivatives.
Excuse me, sorry, I woke up an hour ago.
You're good, I did too. So,
Forward
forward derivatives of the regular trig functions. I would also want to remember derivatives of the inverse trig functions. These three.
This problem's a lot simpler than I thought it was.
Too bad, yeah.
It does require you knowing the unit circle, though. I think, because you have to plug in pi over 3 to tan x, and do I remember that?
See, so
I don't think I remember that.
pretend like that's a circle. Over 6. This is root 3 over 2, comma 1/2. Is 2 over 2, comma root 2 over 2.
Oh my god, I forgot how those. Yeah. Okay, so it would be it's just it never goes in. So it'd just be square root of 3 over 2 over 1 over 2, which would just be 2 square root of 3 over 2, right?
Cancel the 2's and you just get square root of 3. This will be 2 pi times 4 pi over 3 minus tangent of pi over 3, just root 3. And then from that we need to subtract what we get when we put in 0, but that's just 0.
Yep. Okay. Yeah, this is a lot simpler than I thought it was.
Yeah, it's really not too bad. The hard part here is definitely the setup. The graph and all these distances, the real challenges here. And don't feel bad. I think people email me and ask me.
So that would be just 2. Yep. So 4 pi over 3 minus the square root of 3. And that's it?
That's it.
Okay. I was busy catching up on the first homework, so I didn't have a lot of time to dive into the dishwasher method. I kind of understand it. For the most part, I understand it. It's just I didn't really understand the R thing. I was really trying to understand like how to do the R thing. But I guess there's the DV formula that makes a lot more sense the way you just explained it, which is just the high Y value minus the low Y value.
Sorry, finding.
It seems that there's a pattern of upper minus the lower here. So
You just have to correctly identify what is upper and what is lower. And sometimes if we're doing a side-to-side thing too, we might end up.
Y, and I know that right equals top and left equals bottom.
The association.
Yeah.
Think about it in terms of distances like this. Always be safe.
That makes sense. Yeah. It definitely makes sense. Which other one was throwing me off? I was looking at this volume one for Well, both the volume ones were kind of confusing looking on homework too for 6 and 7. Mostly 7, I think.
I might have time to do one more, but then I'm going to have to. Which would you like to do, 6 or 7?
I think 7.
They're both pretty tricky. I see here, look under the modules in Canvas. You have a bunch of links to like videos and people solving these sort of problems. I think you might find that helpful. Go ahead and see if we can sort out number 7 here. So we want to find of the sphere. Best to draw this. The sphere is R, and the height of the cap is H. Here's what we're trying to do, right?
Yeah.
So the first time I did this in the class, this as a dishwasher problem. The second time I did this as like a straight slicing problem. Both of them are kind of tricky. The easiest way to get it conceptually is to get this as a solid of rotation. So all of the solids that we've been playing with are coming from creating a region. Here, if I imagine taking a circle of radius r, centered at the origin, rotating it about the y-axis, generate the sphere, right?
Yeah.
What portion of this circle will I have to rotate in order to generate this?
I couldn't quite make out what you just said there.
So here, if I rotate the shaded region on the right, I will get the shaded solid on the left. If I rotate just this half of the sphere. Does that make sense?
Yeah.
This distance here is h. This distance here has to be r minus h, where r is the radius of the sphere. Where here is r comma 0. Here is 0 comma r. That's going to be the game. We're going to rotate the shaded region about the y-axis and the volume generated. To do that, I'm going to need the equation for this circle. I'm also going to need to set up like a disclosure type thing. So I'm going to redraw the quadrant 1 piece there. I'll redraw the whole thing down here nice and big.
Okay. So wouldn't it just be like the area of a circle divided by like 4?
I wish. It's not that simple. Because this is the area of one piece. I'm not really looking for an area here. I'm looking for a volume. So it's going to be like a disclosure thing.
Okay.
So I start with the equation of the circle, which is y squared plus x squared equals r squared. I'll redraw this nice and big here so we can get in and label our distances. going to rotate to get my cap. This is H. This is H. If I solve this equation, and I'm rotating about the y-axis, I'm going to use my disk washer method. That means I need to draw my stripping like this, particular to the axis of rotation. Here's my region. Here, no little r, is all the way to the axis of rotation. Little r in my formula for dv is 0. To rotate this guy, I will need the distance from the end of the strip to the axis of rotation, which is the thing we usually call r, which means I need to know what this looks like in terms of x and y. I'm going to take this equation and solve it for x. This is the same as saying x is the square root of r squared minus y squared. Really, I get a plus and a minus when I take that, but I'm dealing with the semicircle here. I don't care about what's going on down here. The positive square is okay. Which means that this right as root squared minus y.
Okay. That makes sense. I don't think I'd ever come to that conclusion myself, but that makes sense.
These are definitely the two harder problems homework. And I would expect it to take some time to get this observation. I think that you could get there. Especially if you've solved all the other problems in that homework recently. There are a few times where we need to characterize a point curve in terms of one variable or another. Ask you this, do you know why I did it like this instead of calling it square root r squared minus x squared? I do this in terms of y.
Yeah.
This thickness, the thickness of the strip is a dy thickness.
Yeah, we're yeah. That makes sense. The part that I think I would I would have had trouble remembering would have been the formula for a circle.
You do want to bake that into your brain. That's one of the important ones. Like kind of everybody knows the formula for a parabola.
Yeah.
Also know the formulas for the circles. You'll probably blame that on me and our weak treatment of conics in pre-calc. I will take the blame for that. Maybe after we finish this problem, I'll give you a few of those formulas that you can bake in your head. From here, distance is this x value. It's the distance from the y-axis, which is x equals 0, this curve. Horizontal distance would be this x value minus this value here is 0. X value minus this x. So r is just the square root of r squared.
That makes sense.
And dv is pi times r, big R squared minus little r squared. The little r in our dv is not the same as the radius, though. I don't want to write that down and make things confusing. Have
Which would just be pi r squared minus pi y squared.
yeah. even write it like that because we're going to want to pop the pi out of it.
Yeah, pop the pi out, yeah.
And v is going to be the integral of dv. To figure out to integrate from and where to integrate to. The smallest y value in my region is minus 8.
You're integrating from r to r, or from negative r to r?
Unfortunately, no. I'm going to integrate from this y value to this y value.
Okay, so from 0 to...
It'll be from r minus h to r.
Okay. Why?
Look back at the problem at how they labeled things. The height of the cap itself, radius of the sphere is r. The height of the cap, that's this.
I see. Okay, so our axis of rotation is, or where the line lies is, okay, that makes sense. That makes sense.
This horizontal line right here is where the cap of the sphere is being cut.
If our height of r is r, then the height, or the height minus the yeah, okay, that makes sense. That makes sense. Okay.
This will be pi times squared minus y squared.
Yep, okay, and then we have, is it okay to have two variables here?
Well, remember the r here is a constant. It's the radius of this circle.
Oh, that's right. I forget that r is a constant. It's okay. So
If it wasn't a constant, that would be trouble.
okay.
So it is constant, we're good. Squared will integrate to r squared y.
So r cubed over 3.
Careful, careful. R is a constant. We're integrating dy.
Oh shoot! Again, yeah, you're right. You're right.
Y.
So r squared y minus y cubed over 3.
Good. And we evaluate this mass minus h to r.
Is that, how do you, excuse me. I'm just so do we just plug it in as normal? So like top minus the bottom?
Plug in the top, and then we'll subtract from that what we get when we plug in the bottom.
Okay.
This is going to look like times in squared times y becomes r cubed and minus y
R squared, it would be r squared r minus r cubed over 3. Yeah. Which would just be r cubed minus r cubed. Yep. Okay. Yeah. Minus r squared times r minus h minus, yeah, r minus h is cubed over 3. Is there a way to simplify this?
Yeah, for sure.
So it'd be r cubed. So that stays the same. That all stays the same pretty much.
So these are like terms. Right? These are both.
But you can subtract.
Yeah. R cubed minus 1/3 r cubed. Third cubed.
No, shoot, you're right.
That one's not too bad. Over here, get a little bit hairier.
I was thinking, yeah, because you're gonna have r cubed minus r squared h. If you simplify that out, I think. Then you're gonna have, oh boy, I don't know that one in my head. I don't know r minus h. Like, if you were to like multiply that out, what would that be? Does it matter?
I mean, yeah, it would be nice to play with it, but let's minus h cubed. This is from the binomial theorem. This is cubed plus 3r plus 3r RH minus H H minus cubed. And you can FOIL it all out. Throw on the FOIL until you get there.
Okay.
To do that, I mean, you can input this answer and it would be okay.
But we don't need to.
Right. Yeah, you could just leave it like this. That would be all right.
Okay.
If you wanted to, you could keep going. A times minus third times you can distribute the 1/3 and see if there are any. If there are, there's the r squared h term. Able to combine. There will be some r cubed stuff, and I've got 2/3.
So it'd be negative 1/3 r cubed plus, oh boy, there's a lot of other stuff.
Right. Just even come along for the ride. We'll see what we get. I have plus 1/3 r cubed.
So it'd be back. It's back to 0 r cubed, which should just be, it just cancels out, right?
Yeah. And then I'll have 1/3 times negative 3 r squared h minus r squared h. Will cancel also. And then I'll have plus h squared minus 1/3 h cubed.
Okay. So the 1/3 r cubes are gonna cancel.
Yeah, these look like they're gonna go.
Yeah.
These look like they're gonna go.
And so you're just left with rh squared minus 1/3 h cubed.
That's correct.
Okay. It's a lot more complicated than I thought it was gonna be.
It is a little bit. It is. Like I said, if you wanted to leave it here, this would be okay.
Okay, that would be okay. If okay. I like the neatness of the last one though.
There might be other ways to attack this algebraically. I think that's probably the fastest way.
So would that be the volume? Like if you were to plug any height into that, would that just be the height? You could find the volume of any height in the circle from that point?
You'd be finding the volume of the sphere. For example, if I were to plug in h equals 0, I should get 0. To plug in h equals r, I should get the volume of half of the sphere. And if you were to plug in h equals 2r, you should get the volume of the whole sphere. For fun, let's plug h equals r. Sorry, what did I write? H equals r.
Oop, I can't see it.
Sorry. Plug in h equals r, you get the volume of a sphere. What is this? It would be times
So
r,
it'd be r cubed
r cubed minus
minus 1/3 r cubed.
is a times r cubed. The volume of the sphere is
So
1/3 r cubed. This is exactly half that.
that's really cool.
Isn't it? It's neat. So let you find the volume of fractions of a sphere you're measuring by height. Kind of thing, but it's useful. You're talking about like a tank. Can you imagine like a tank of water made out of a sphere? This is the place where the height of water will tell you how much water you have if your tank is spherical. So things like that can be a utility for this.
Okay.
right?
Well, thank you so much for your time. That I mean, I think unless you can do more,
I'm gonna have to get going. I've got a couple other things I gotta knock out today. More after tomorrow if you're free for the office hour.
That's Friday, right? Friday's office hour. Do I have anything? I don't think I do. Mondays are normally good, and then Fridays are normally good, except on Monday I accidentally overslept because my alarm didn't go off, or it did. It just went off in my wireless headphones that I didn't disconnect.
And stress. But yeah, if you want to come by, I'd be happy to see you there. Otherwise, if you want to meet up some other time, just send me an email.
Okay. I obviously I didn't finish homework 2, which would then in turn mean I didn't finish homework 3 or any of the other ones. I've been really trying hard to like study this stuff as well as like finish the homeworks.
Let's make sure everything is that you could be working on. I see. There you are.
I think I got about halfway through this one.
Okay. And then I'll just pop all of these open for, so it looks like homework 1 is all the way done. Homework 2, 3, and 4. I'll push all those to the 19th.
Thank you so much. I'm gonna get started on those today. I gotta go shopping because I had to get my parents to come down here because I don't have a vehicle and they live 2 hours away and I have no real access like to any transportation because RTS is shut down. So they're coming down to help me get food.
Sweet.
So after that, I'm gonna hop on and try and finish out all this math and study up.
Sounds good. And if you run into any questions, don't hesitate to email me or Canvas message me. If time for a meeting, you can always take a picture of your work and send that to me, and I can let you know what's going on.
Of course, awesome. Thank you so much. You recorded this, right?
I did not. No, I don't think so. I didn't have this one set to record automatically.
It says recording in the top right or top left.
Let me pop out of here and see if I have recording controls. Oh shit! At the auto record. Would you like me to put this to YouTube for you?
Yeah, if you could upload it to YouTube, so I can look back at this when I do the circle problem. That would be awesome. I took notes on it. It's just my notes are terrible.
Shit. I'll start uploading this. It's gonna have to take a second to process, but then I'll send it to you through email.
Of course, awesome. Thank you so much.
Look, have a good afternoon.
You too. Bye.